Hello everyone. So I am one of the instructors for the Python machine learning techniques team. So good to see all of you here and also some of you online. Yeah. So the kind of bottom line of this talk is that I'll be looking at some very elementary aspects of So I'll be looking at some very elementary aspects of mathematics. So one attitude that I would request all of you to take is that assume that you are still school children, right? High school or maybe even before primary, right? So uh, you'll have to think about it that way. So whatever I'm presenting is nothing new. In fact, it's very simple. And the whole point is how can we understand some of these very simple concepts from a visual perspective, right? So there'll be four themes. The first one is concrete to abstract, and we have a few other themes. But the underlying the glue that connects all of them is that we look at them through a different perspective, images, right? So how can we look at math through this different way, right? So the first theme is going to be, so is this, there a way I can close this? Just give me a second. Okay, so it's still visible, right? Okay. Yeah, so, okay. Right. So what happens is, let's say if you are in a primary school, right? And the only thing that you know is 2 into 3 equal to 6, right? And you've just started learning multiplication tables, right? And then I come and present you something like this, right? 1324 into 3791. Now this is, you'll be thrown off, right? If you're a kid, you'll be generally thrown off by something like this. And if I uh, go ahead and tell you that the multiplication of numbers is commutative, right? So the order doesn't matter. Now, to be very honest, this is completely non-intuitive for a kid, right? So why should the order matter? Why should the order not matter, right? It's a very important question. I think we don't ask it too often. So for example, if I say that 2 into 7 is 7 into 2, most often it's because you have memorized the multiplication table, right? 2 sevens are 40, right? This is something that comes from memory. And you say that 2 times 7 is equal to 7 times 2, not because of, knowing the commutativity of integer multiplication, but more so because you have memorized the multiplication table, right? And this is true of, I think, most of us. So how do we, present this whole idea to, say, children, right? So one very obvious way is to arrange numbers in the form of a grid, right? And you have 3 into 5 is obviously row times column, right? So you have 3 rows. Multiplication is nothing but repeated addition. So you have 3 rows of the same number of balls, let's say blue colored balls, and you have, that's your idea of multiplication, right? So now how do we go from here to the commutativity? Instead of looking at it from, say, top to bottom, right? I assume that you're looking at it from top to bottom. You just rotate your point of view and you get 5 into 3, right? So this is a very simple way to illustrate the commutativity of integer multiplication, right? So why does the order not matter? Why it shouldn't matter? So this is one way in which an image can be of great use. And the point I'm trying to make here is that we must, when we are teaching students mathematics, we must always go from the concrete to the abstract, right? We must not, immediately say that, okay, A into B equal to B into A. No, let me show you some examples. A equal to 5, B equal to 3, right? So that's going from the abstract to the concrete. We should rather go from the concrete to the abstract. So this is a picture that students will very easily be able to grasp, right? Now, from multiplication, if we immediately jump to, say, geometry, we say that area equal to length into breadth. Now, how many of us have really thought about why area of a rectangle should be B into N? Right. So if you divide it into grids, right, you still end up with a smaller rectangle, right? So why is that rectangle's area? Right. So there is some kind of an axiom operating there, right? You assume that a unit square has area 1. But for a kid, how do you, so children don't understand axioms, right? So you need some way to motivate the whole thing. So we just have shown them how multiplication works, right? Now, area of a rectangle is also the same multiplication. So what's happening here? So I'll just give you a quick visual for this, right? So area is what? Amount of space that is contained in a region. So how will I teach a kid to do this, right? I'll just tell him or her that, the first rectangle here contains, say, 4 rows of 3 balls each. So there are 12 balls in that space. Now the one on the right has more number of balls, therefore more area. And you can see very immediately how this leads to B into L, right? So these are, this is what we say that when we move from the concrete to the abstract, right? So this is another example. So if we move from rectangles, and since we are talking about areas, it's very natural to think about pi, right? So circles. So if you want to compute the area of a circle, the obvious thing that you need is the value of pi. So if you think about how the ancients actually came up with the good approximations of pi, this is one of the algorithms that has been there for a very long time. So this is called Archimedes algorithm. So what Archimedes did was the following. So you take a circle and then you inscribe and circumscribe polygons, regular polygons, right? So these are all regular polygons that you can see here. There's a pentagon, hexagon, and so on, right? So again, your idea of limits comes into picture here, right? So if you can inscribe and circumscribe polygons of increasing size, right, that will of itself take you closer and closer to the area, right? So you're essentially sandwiching your circle between two sequences. Okay, so your idea of sandwich theorem, the whole limits of sequences, all these our ancients, they already did it. So I don't want to go too much into the specifics of Archimedes algorithm, but this is what Archimedes did. So he started off, I mean, if you want to understand it as an algorithm, he started off with the hexagon, okay, circumscribed and inscribed it in a circle. And then he went to 12 sides, so 12 gone, and then 24 gone, 48 gone, 96 gone, right? So 96 gone is a regular polygon with 96 sides, right? And this is the level of approximation that he achieved. And you see that our very familiar 22/7 crop up here. And this algorithm stood for nearly 1,000 years, right? So you can see how powerful this was. This stood for nearly 1,000 years, after which infinite series came up to replace approximations of pi, right? We had much more stronger approximations by the way of infinite series, but this algorithm stood for nearly 1,000 years. Okay, again, I'm just trying to talk about how we move from concrete to abstract, right? So one very critical question we have to ask is, how did we even arrive at the ideas of areas, lines, circles, right? How did mathematicians, say Greek mathematicians, Indian mathematicians, several thousand years back, how did they arrive at this whole idea of geometry? So the answer to that is nature, right? So if you think about lines and angles, from where do we get our ideas of lines, angles? Any ideas? Which aspect of nature inspires us to think about lines? Okay, Earth, right? So some obvious other answers are, I'm just pointing them out, right? So the sun's rays are, so you get your idea of straight lines from the horizon, from looking at the horizon, right? Tree trunks are vertical, right? What about parallel lines? One very good example of parallel lines is our own human body, right? Your limbs in their natural position are parallel. So these are concrete examples from which ancient Greek mathematicians and Indians abstracted the idea of geometric objects, right? The other thing is symmetry, right? So symmetry is a extremely powerful idea in mathematics. From where did it come? Probably from the human body, right? Human body is an extremely symmetric figure, right? You have axial symmetry right there, right? So and then you have the basic shapes. So the circle would have obviously been, derived from the sun and the moon, right? You don't just wake up one day and start doing theorems on circles, right? First, you must have the idea of what a circle is, and this is where it would have come from, right? So if you just extend it forward, you get your whole, idea of calculus, right? So if you look at integration, it's basically two ideas put together: the area of a rectangle and the idea of limits, right? So you start with a finite number of rectangles, and then if you suddenly blow them up, you have your integral, right? So that is the basic lesson that we take away from this. So that was the first part of the talk. So the next few minutes, I'll be talking about another theme again through the lens of images. So this is about similarity and congruence, right? Again, very simple formula that we have been used to since 7th or 8th standard. Okay, so this is the nth triangular number. So does anyone know why it's called a triangular number? Okay, right. So this is one reason why it's called triangular numbers, right? So you have the first triangular number, and then you have 1 plus 2, you have 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, right? So it's obvious why it's called a triangular number now, right? And what I'm trying to convey here is that these are things that we should say right at the school level. Right? So even before you introduce the concrete version of this formula, as though this is something you have to memorize and mug up and regurgitate in an exam, that should not be the case, right? So the moment, even before you mention this formula, what should be there in front of you is an image like this, so that I never forget what triangular numbers are. Okay. So if you think about it, what kind of triangles are these? If you just join the diagonals, the diameters, these are all equilateral triangles, right? So you can just change the orientation and make them right triangles. They are right triangles, but right isosceles triangles, right? So now the whole aspect, what we are trying to do is how do we get to the formula n into n plus 1 by 2, right? So we'll use the idea of congruence here. So think about this. This is the sum of the first four natural numbers. Now what I do is I use congruence. Like this is also the sum of first four natural numbers. I join them together. Okay. So if you remember from the multiplication slide that we saw before, this is nothing but rows times columns, right? So this is T4, it will be 4 into 5, but you're adding them twice, right? So you get n into n plus 1 by 2, right? So this is a very visual way of seeing that sum of the first n numbers is n into n plus 1 by 2, right? So this is the another example. So we are now summing the odd numbers. Now, if you have not seen this, I mean, I'm sure most of you would have seen this before, but if you have not seen this before, this can be a very surprising fact, right? You have sum of odd numbers on the left and you see a perfect square come up on the right, right? So here's a very quick animation of what's happening, right? You start with 1 and then you have 3 squares and then you have 5 squares, right? So these are the 3 odd numbers and you're going to sum them, right? So there's a small trick that you're doing, uh, which will become apparent soon, right? You just move these squares up, right? And you create this kind of a pattern, and then the 1 plus 3 becomes 4, and then 1 plus 3 plus 5 becomes 9, right? So this is again a very visual way of seeing that the sum of the first k odd numbers is equal to k squared, right? I'm going to play it again, so let's move on. Now, what we do for finite sums, we can also do for infinite sums, maybe not with that effect, but this is a very popular geometric series, right? So we again learn this in, say, 8th standard. We learn the formula that if the common ratio of a geometric series is r, then the result is 1 by 1 minus r again, right? So typically we start with that and then we plug in the value of r equal to half, and then we say half by half is 1. But there is again a geometrical way of, a visual way of seeing the whole thing. So you start with a square. Sorry for the lag. There is some lag here. So you divide it into half, right? So that's your first term of the sum, and then you divide it into one more half, that is 1 by 4, second term of the sum, right? And then you go and do it one more time, you get 1 by 8, and I hope you see the pattern, right? So this is half plus 1 by 4 plus 1 by 8, so on. So that is one more case. And third one is kind of interesting. Again, a very simple result, elementary result. This was shown by Galileo way back in 1615. If you take the sum of the first k odd numbers and divide it by the sum of the next k odd numbers, the result is always the same. It's 1 by 3. Okay, so you have sum of first 3 odd numbers here, 1 plus 3 plus 5, 7 plus 9 plus 11. So this seems to be a very interesting fact. Again, very trivial but interesting nevertheless. So this is one way to prove this. Okay, so I have the first few odd numbers here, 1, 3, 5, 7, 9, 11, 13, 15. Okay, divide it into first 4 odd numbers and next 4 odd numbers. So what we are trying to say is sum of all these circles, total number of circles here divided by total number of circles here is 1 by 3. That's what we are trying to show. This is how it was shown, right? So this is one very elegant way of showing that the sum of the first k odd numbers by sum of the remaining k odd numbers is equal to 1 by 3. So you see here that there are, again, you can connect this with geometry, and there are 4 equilateral triangles. If you think about it, there's one big equilateral triangle and there are 4 congruent triangles, right? All equilateral. So we again extend this idea, right, and quickly go to an infinite sum. Okay, so I want you to relate this infinite sum to the image that you've just seen here. So this is 1 by 4 plus 1 by 4 square, another geometric series, and this is also equal to 1 by 3, right? So notice this beautiful connection between this image of 4 equilateral triangles and this one. I'm again going to play a very short demo, right? You have an equilateral triangle of unit area. Okay, this is unit area, and I'm dividing it into, now you can see that there are 4 congruent equilateral triangles, right? Each having area 1 by 4. So 1 by 4 is the first term in our series. So I'll just continue this pattern. Okay, so now you have divided this, right? So this is 1 by 4 square. Okay, so you have divided this smaller equilateral triangle. Now we come to similar triangles, right? These are all similar triangles. So if I keep continuing this pattern, I'll have 1 by 4 cube coming up here, and then 1 by 4 power 4, and so on and so forth, right? But what we are looking for is the sum of these terms. So how do I do that? Notice that this is 1 by 4. This is 1 by 4 square. This is 1 by 4 cube, right? And that is 1 by 4 power 4. So this is the left side of the whole track. Now we can do something similar for the right side. So these are all the same, right? So this is also 1 by 4. Now this is 1 by 4 square. The other one is 1 by 4 cube and 1 by 4 power 4, right? And just push this here. So notice that you have these 3 tracks. All 3 tracks represent the same infinite series, right? So you have 3 such tracks, and all of them sum to the whole triangle. So it is 1 by 3, 1 by 3, 1 by 3, right? So that is how you come to the arrive at the formula of this infinite series. Again, we see the power of very simple ideas such as similarity and congruence in action here, right? So that is the second part of the talk. I think roughly 2 more minutes remaining. I'll quickly. So this again, very briefly, we jump into combinatorics. So you have n choose 2. I'm sure you all know what n choose 2 is, right? So from n objects, how many ways are there to choose 2 objects, right? The formula is again n into n minus 1 by 2. So obviously, it's very easy to derive this formula. So that's not using algebra, right? I'm not interested in that. So again, we look at a visual way of understanding n choose 2, right? So assume that, so why am I drawing this triangle again? Because what you have on the right is again a triangular number, right? It's the sum of the first n minus 1 natural numbers, right? So I'm having this kind of a triangular setup. So there are about 7 marbles here. So I'm essentially trying to do 7 choose 2, right? I'm trying to come up with an idea. So first we color them blue, okay? And then we color all the others green. So here is the nice thing about this image, which is that for every pair of blue marbles, you have exactly 1 green marble associated with it, right? And likewise, for every green marble, you have exactly 2 blue marbles associated with it. Okay, so if this is not clear, we can number them as 1 to 7, right? And these 2 blue marbles are associated with this green marble. So it's 2.6, right? And you can just complete the whole picture. You will get something like this, right? So what are we essentially doing? If you assume that G is the set of green balls and B is the set of pairs of blue balls, right? By pairs, I mean 3 comma 4 is a pair, 4 comma 3 is not a, it's the same pair, right? So it's an unordered, it's not an ordered pair. So what do you think the function from B to G is? Whatever function I've shown you. What kind of a function is it? Every 2 blue balls is associated with exactly 1 green ball, and vice versa. Okay, so in the interest of time, I'll just So the F is a bijection, right? So that's what a bijection is, right? So every element in one set, you are mapping it to exactly one element and vice versa. So this gives us a unique way of counting. So the number of blue balls is n choose 2, number of pairs of blue balls. The number of green balls is just a triangular number, right? So it's n into n minus 1 by 2, right? So this is one way of proving it. So that's what I call the bijection bridge. Finally, there's one last theme in this talk, which is a story proof. I very quickly run through this because I have just 4 more minutes. So story proofs are nothing but combinatorial identities. We have heard the term before. So if you have an identity like this, right, n choose k is n choose n minus k, right? So you can do it algebraically, meaning n choose k is n factorial by whatever, right? And then you can cancel terms out and then you can show that this is true. But that's not very insightful. So what we have is something called a story proof, where you construct a story, right? So let's take this particular example. We have a switch, right? Switch can either be an off or on state, right? Now start with everything off, right? And I want to do phi choose 2, right? Phi choose 2 is what? Number of ways in which I can switch on 2 of them, right? Now, this is exactly the same way as saying that everything is on and you want to switch off 3. This is just n choose n minus k or phi choose 3, right? So this is just one way of seeing that. The second identity that I would like to cover is this one. N choose k is whatever is given there, right? So this is one identity. Now, how do you show this using a story? Okay, so assume that there's a competition and several people are competing and you are also one member here. You are the blue person here. Okay. So let's say there are going to be 3 winners, and you could either be optimistic about your chances, right? In which case you always win a prize. So how many ways are there to select 3 people who will win a prize? You are always going to be there. So this k minus 1, right? One prize is going to go to you always. And from the remaining n minus 1 people, you have to choose k minus 1. So this is n minus 1, choose k minus 1, right? The other way of thinking about this is, you can be pessimistic and say that I'm not going to get any prize. So you are excluding yourself out of contention, right? So from n minus 1 people, you are choosing k prize winners. Okay, so this is the identity that we have shown. So n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k, right? This is one way of showing it. One more identity. This is again a very common identity that we have seen. So is the screen still visible? No. So how do I do this? So you have to pick a team. Let's say you have to pick a cricket team. You have 15 members in a squad. So there are 2 ways of picking a team. One is you first pick the captain, right? The moment you pick the captain, he's also there in the team, right? Now you have to pick the remaining 10. How do you do that? So there are n ways to pick a captain, and then pick the remaining, there are n minus 1, choose k minus 1, right? So total number of ways is n into n minus 1, choose k minus 1. This is one way of doing it. The other way of picking a team is that you could choose the k players, okay, and choose k ways of doing that. And then you could pick a captain from one of them, right? So there are k ways of doing that. Okay, so that is k into n choose k, right? So these two are essentially same. Okay, so that is one, and this is the final example with which I will end the talk. So it's called Vandermon's identity, quite useful one in combinatorics. So again, so this is the statement of the identity. How do we prove this using a story, right? So a visual story. Okay, so on the left hand side, you see that there are n plus n people, and you have to elect k members from this, right? It's an election story. So there are so many people here, right? And you have to choose, say, 5 of them. How do you do that? That is what it is, right? M plus n choose k. Now, if you notice, there is an intrinsic order here. So there is a way you can categorize people as green and blue. Let's say green men and blue women, whatever, right? So once you categorize them in this way, you can now choose, say, R of them from one category and k minus R from the other category, right? So, and the product of this is the number of ways of choosing k, right? And this you have to obviously sum over all possible values of R, right, from 0 to k, which is what this identity is all about, right? So n plus n, you divide it into 2 groups on the right hand side. On the left, you don't do the division, right? So these are called combinatorial proofs, and another way of calling them is story proofs. So that's what I really had. So it's a different way of looking at mathematics, which uses uh, visual ideas, right? So yeah.
You can ask your questions.
Okay.
Any question from audience?
Any questions?
Division only.
So
Yeah, stand for division, remainder, very different.
right. So yeah,
Okay, not expect.
maybe we can come up with something good for that one. Oh, anyway, yeah. So thanks.
Thanks, Karthik, for this wonderful talk. These are really nice. Should share it with all of us.